Hai, Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera for the panels. For today, our group will present for our FSG 311 project, which is the title is Optimizing the Solar Panel Performance, Investigating the Effect of a Sunlight on the Energy Output. For our supervisor is Dr. Roshaini binti Afandi Zaman. The introduction or preview for our project. As we know, the sun is a limited source of energy, providing more solar power in just one day for the entire world. As a clean, sustainable, and pollution-free for resource, solar energy is an ideal renewable alternative. This project is focused on the improving solar panel by performance, studying and the effect of light source angle and height on the energy output. Also, since the solar panel efficiency depends heavily on the sunlight angle, which change with the location and season, finding the optimal orientation can significantly enhance the energy for the capture for the photovoltaic of the panel solar. In this research, we aim to explore two key questions. First, what are the optimal moments for maximizing the efficiency of the solar panel under the natural light condition? Second, how do different types of light source affect the energy conversion efficiency of the solar panels? The goal is to understand how solar panel perform at various times of the day as sunlight intensity and angle change throughout the day. By determining the most effective time for the energy capture, we can optimize solar panel efficiency and improve energy production. This study will provide valuable insight into how natural light conditions impact the effectiveness of the solar power system. For this project, our objective is to examine how different types of natural sunlight affect the voltage, current, and power output of the solar panel. As the intensity and angle of sunlight change throughout the day, we expect this variation to impact the solar panel performance. By studying this effect, we aim to determine the optimal condition for maximum energy output. This research will help improve the efficiency of solar panels, ensuring the better energy production and making solar energy more reliable source.
So the first one is the solar renewable energy. So according to the Jamal M. Alabid 2020, solar renewable energy is environmentally friendly technology, a great energy supply, and one of the most significant renewable and green energy sources. The second one is the environmental benefits of solar energy. Rabaya 2021 said that examined the advantages and disadvantages of solar technology in relation to the environment. Solar panels contribute to climate change by drastically reducing air pollution and carbon emissions. The third one is the maximizing solar PV efficiency. According to El Hamoumi 2022 said that investigate the evolution of solar PV systems from the material used in their design to advanced method that improve energy output. The fourth one is impact of locations and tile angle on solar PV panels performance. Yunus Khan 2019 said that investigate the effects of solar PV panel location and tile angle on performance. According to the study, energy output is greatly increased by modifying the tile angle according to seasonal variations and geographic locations. The last one is modification of solar panel. According to Q Jung Che, 2021 said that construction of solar panels in particular is more technologically invested than other solar panels processes due to the effects of any unpredicted or neglected soil or land factors on the system's consistency, efficiency, and the performance over its lifetime.
In this experiment, we utilized several key materials to evaluate photovoltaic system performance. The primary component was an 18-watt monocrystalline photovoltaic panel designed to convert sunlight into electrical energy efficiently. We paired this with a solar charge controller to regulate the voltage and prevent overloading. Additionally, we employed a solarimeter to measure sunlight intensity, ensuring precise performance assessments. Finally, a multimeter was used to monitor critical electrical parameters such as voltage and current. Together, these tools allowed for comprehensive analysis of the system's efficiency. To analyze the behavior of the solar panel, we set up the PV system with the panel connected to a solar charge controller which regulated the energy flow. A multimeter was used to measure the current and voltage outputs. The panel was positioned at a 0-degree angle and data was recorded every 30 minutes over a 3-hour period. We calculated the power generated using the formula power equals current multiplied by voltage. This experiment also explored how different times influence the system's performance. Here is the experimental setup. As you can see, the photovoltaic panel is connected to the solar charge controller, which regulates the voltage and current. The multimeter is attached to monitor electrical output, and the system is set up to capture solar energy efficiently. This visual representation provides clarity on how the components were interconnected during the experiment.
The solar irradiance affects both the current and voltage output of the solar panel, which means it plays a crucial role in regulating the power output of the panel. We have presented the results for current, voltage, power, and irradiance at various times with a fixed angle at 0 degree in the table. The result of power came from multiplying the current with voltage. The solar panel's performance was evaluated by monitoring current, voltage, power, and irradiance throughout the day at a fixed angle of 0 degree. Between 11 a.m. and 11:30 a.m., the current rose from 0.54 A to 0.6 A as irradiance increased from 675 watt per meter square to 780 watt per meter square, leading to a power output rise from 10.53 watt to 11.1 watt, despite slight voltage drop from 19.5 volt to 18.5 volts. For a midday peak performance, by 12:30 p.m., the current peaked at 0.72 A, achieving a power output of 13.18 watt. This performance was achieved despite irradiance dropping to 690 watt per meter square, indicating efficient utilization of the available sunlight and stable voltage, which is 18.3 volts. After midday, there is a declining irradiance caused by the current and causing the current and power output to reduce. At 1 p.m., dim sunlight resulted in a sharp drop in current to 0.36 A, with the power output plummeting to 0.2 watts. The current, however, increased to 0.75 A at 1:30 p.m., although the voltage dropped to 17.5. The power reached the day's peak at 13.32 watts under slightly lower irradiance, which is 960 watt per meter square. This was due to the consistent current 0.74A and stable voltage, which is 18 volts. The IV curves graph the relationship between the current and the voltage for a solar panel at different times. These curves provide insight into how the panel's performance changes with varying irradiance and operating conditions. Each curve represents the performance at a specific time, showcasing how current changes as voltage varies. The peak current of 0.75A occurred at 13:30 p.m., accompanied by a voltage of 17.5 V. This indicates a strong solar irradiance and optimal energy production during this period. Then come the lowest current of 0.36A being observed between 13:10 p.m. to 13:15 p.m. The current drop was caused by a cloudy weather, reducing the irradiance and thus limiting the current generation. The solar panel performed at its best during mid to early afternoon, aligning with high solar irradiance. This is the period when usually the current and power output were at the highest, as captured by the graph. In the early morning, both current and power were lower due to the weaker sunlight. There was a temporary decline observed due to overcast conditions, reducing the solar energy available for conversion. The IV curves shows how current responds directly to irradiance, with fluctuations in sunlight causing significant changes. Changes. The voltage remains relatively stable, but it slightly decreases during peak current times, as shown by the 17.5 V reading during the peak of 13:30 p.m. The PV curves plot power output against voltage to show the panel's performance at specific times. These curves highlight how power generation changes under varying sunlight conditions while voltage adjusts to optimize output. The peak power of 13.32 watt was achieved at 14 p.m. with a voltage of 18 V. This represents the highest energy production corresponding to strong sunlight and stable conditions. There is a power and voltage drop around 12:30 p.m. to 13 p.m., which the power decreased from 13.18 watts to 6.48 watts, and the voltage dropped slightly from 18.3 V to 18. This reduction was caused by cloudy weather, which limited the solar irradiance and therefore the panel's power output. There is, however, a rapid recovery of power that was increased significantly as the sunlight intensity improved. Considering that the clouds had cleared, which restored the optimal panel performance. It shows that the weather has impact on this experiment. The drop in power during cloudy conditions around 13 p.m. to 13:30 p.m. emphasize the importance of consistent irradiance for maintaining high energy production. This rapid recovery at 13:30 p.m. shows how sensitive the panel is to changes in sunlight. While power fluctuated due to changing irradiance, voltage remained relatively stable, only slightly varying between 18.3 V to 18.0 V. This stability helps the panel maintain efficiency. The PV curves illustrate how the solar panel's power output changes with voltage throughout the day, reflecting the impact of weather and sunlight intensity. Based on the data of the conducted experiments, the solar panel received the most sunlight at 13:30 p.m. with irradiance peaking at 990 watt per meter square and the current reaching 0.75 A. This indicates optimal solar conditions, allowing the panel to generate maximum current. At 13 p.m., irradiance decreased sharply from 690 watt per meter square to 519 watt per meter square, causing the current to drop from 0.72 A to 0.36 A. This decline was due to clouds blocking sunlight, reducing the energy available for conversion by the panel. There is, however, a rapid recovery at 13:30 p.m. The irradiance and current quickly increased to peak levels, demonstrating the solar panel's responsiveness to changing sunlight conditions. The power is calculated by multiplying the current and voltage. While the current has the most significant impact on power, the voltage also plays a role in determining the final output. The highest power output of 13.32 watt occurred at 14 p.m. under slightly reduced irradiance but stable voltage. This shows how the panel optimized power generation even with slight variations in sunlight intensity. The irradiance directly affects the current, as higher sunlight intensity generates more electrons, increasing the flow of the current. This was evident when both irradiance and current peaked at 13:30 p.m. While voltage has less variable than current, its adjustments influence power output. Even small drops in voltage, such as during high current conditions, can slightly affect the overall power. The data highlights a strong correlation between irradiance and current, with clouds significantly reducing the performance. The solar panel's ability to recover rapidly after cloudy periods shows its efficiency in utilizing available sunlight. Although the current is the primary driver of power, the stable voltage observed throughout the experiment also contributes to efficient energy production.
The conclusion for our finding, the timing of the sunlight on the solar panel is crucial for optimizing their energy efficiency. By adjusting the factor like geographic location, seasonal change, and environmental condition, we can significantly improve energy output. This research focused on identifying the perfect time of the sunlight to enhance solar panel performance, ensuring better efficiency and economic feasibility. Our findings demonstrate that the timing of the sunlight has a direct impact on the energy generation, confirming that the selection of the optimal time is essential for the maximizing efficiency. This study not only addressed the key research question but also contribute to advancing renewable energy solution, making solar power a more reliable and sustainable resource for our future.